Hey everybody, it's Mrs. Harbin and we're starting video note 6.1. So welcome to the mole. So we're going to know what a mole is and how to use molar mass, how to convert stuff using conversion factors and dimensional analysis, and then we can use the mole concept in dimensional analysis to do conversions. So please read chapter 8, sections 8.1 through 8.4 to get an idea of what we're talking about. Okay, so dimensional analysis. Sounds scary, woo, but it's really kind of interesting. So we can convert units from one into another in chemistry, and we do it a lot. And so we call this technique that I'm going to show you dimensional analysis. So using the units, analyzing the units to help us solve problems. Another way to say it is make the units go away to get new ones. So we're going to need to use what are called conversion factors. And a conversion factor is just a true statement that comes from an equality. And we can use it as a ratio to cancel units. So what are some equalities you might know? Well, 1 dozen is 12 things. So we can use that as a conversion factor. 8 legs for 1 spider can be used as a conversion factor. Or 1,000 milliliters per liter can be used as conversion factors. So any equality can be written 2 ways. We could say 12 things for every 1 dozen, or we could say 1 dozen has 12 things, and both of these are just making a ratio out of the true statement. Okay, so we can use ratios, conversion factors of true statements to convert. So we want to change 9.5 years into minutes. Okay, so this is what we're given. This is what we're trying to find. So we're going to use ratios as conversion factors. Okay. Now I don't know how many minutes are in a year, but I do know that for every year there's a certain number of days. Okay. And I also know that for every day there's a certain number of hours. And I know that for every hour there's a certain number of minutes. And so if I follow this pathway, the years are going to cancel out, the days are going to cancel out because it's top and bottom. Hours over hours is going to cancel out, and I'm going to be left with minutes. So as long as I make these true statements, I'll be able to convert years into minutes. So I know that every 1 year is 365 days, every 1 day has 24 hours, and every 1 hour has 60 minutes. So I just have to multiply 9.5 times 365 times 24 times 60, and I would get 4.99 times 10 to the 6th minutes. Now, what's this all about? Scientific notation. It just means that this is a really big number because it's multiplied by 10 to the 6th. Okay, so that's how many minutes are in 9.5 years. Okay, metric conversions. You have to know the ones I'm going to put up. So I want you to know the relationship between kilograms and grams. If you have 4.56, oh, there's a point there, kilograms. So this is what you're given. This is what you're trying to find. There's a direct relationship between kilograms and grams because grams is a base unit and kilograms is has a prefix on it. So there's a direct relationship between any base unit and prefix unit. So I know I'm going to have to get rid of kilograms and change it to grams. Now I have to make this a true statement so that kilograms will cancel out and I'll be left with grams. So what makes this true? Well, I know that there's 1,000 grams in every 1 kilogram. Hopefully you know that too. If not, now you do. And so then I would take 4.56 times 1,000 to get 4,560 grams in 4.56 kilograms. Okay. I need to convert 9,500 milliliters to liters. So this is my given. Usually start with your given. And you need to convert it. And I know there's a direct relationship because this is a base unit and this is a prefix. So I could do this in one step. Milliliters to liters has a direct relationship. And so what's bigger? Well, a liter is bigger. And I know there's 1,000 milliliters in a liter. So now milliliters cancel out and I'm left with liters. And I just have to divide 9,500 by 1,000, 9.5 liters. Okay. What about this? 4.3 centimeters cubed to liters. What, real? So liters is a volume, and so is centimeters cubed. But there's not a direct relationship between centimeters cubed and liters. So this is what I'm given. This is what I'm trying to find. So I'm going to have to change my centimeters cubed into a direct relationship, which is milliliters. And then I can change milliliters into liters. So you might not know, but this is what I'm telling you. 1 centimeter cubed is equal to 1 milliliter. And then 1 milliliter is a fraction of a liter. So we can convert from that. So you always, not always, but often put down what you're given. And we gotta get rid of those units and change them into what we're trying to get to. And then change those units into the final destination. So this is the part I want you to remember, that 1 milliliter equals 1 centimeter cubed. I also want you to remember that a liter is bigger and there's 1,000 milliliters in a liter. So centimeters cubed is going to cancel, milliliters is going to cancel. I'm going to take 4.3 divided by 1,000. I'm going to get 0.0043 liters. Okay. All right, converting is fun. Woohoo! All right, split unit conversions. What? So not all numbers have only one unit. Some have two. I can run, believe it or not, 3.25 meters every second. Right? So you might be wanting to know, well, how many kilometers per hour is that, Mrs. Harbin? Yes, I also want to know. So I'm going to start with what I'm given, 3.25 meters per second. So see what I did there? I took this and I put it there, and then I don't need a number here, but if I wanted to, I could put a 1. So my first number actually has split units on it. 2 units. One's a numerator, one's a denominator. All right, so nothing really changes here, except that now I have to convert the meters, the top unit, into kilometers, and I have to convert the bottom unit from seconds to hours. Okay, so given this, find this. So my plan is going to be turn my meters into kilometers, because I know there's a direct relationship with that. And then I'm going to turn my seconds into hours, but I'm going to go through minutes, because that just makes my life easy. So I need to get rid of meters. I put it down there. And I want to change my top unit to kilometers. I put that there. That'll get me close. Seconds is on the bottom of my starting point, my given. So I need to put it on the top to get rid of it, because it's going to cancel out that way. And I need that to turn into minutes before I can turn my minutes into hours. All right, look at all this. No numbers, but the units guide me. So I'm going to figure out the relationship between meters and kilometers. 1,000 meters equals 1 kilometer. So I'm taking this equality and I'm making this a true statement. So I need to put the number 1,000 with meters and 1 with kilometers. Minutes and seconds. What's bigger? Well, minutes bigger, and I know there's 60 seconds in it. Minutes and hours bigger, and I know there's 60 minutes in it. Look what happens. Meters cancels meters. All right. So on the top, I'm left with kilometers. Seconds, even though it's way over here, cancels seconds. Kilometers, nothing cancels with, so I got to keep that. Minutes cancels out. And I'm left with hours here and kilometers there. All right. Kilometers per hour is what I want. So now I got to do the math. It's going to be 3.25 divided by 1,000, because that's what this fraction bar means, divide by. Times 60 over 1, so times 60, times 60 over 1, so it's times 60. So I find out that I'm actually running 11.7 kilometers per hour. Pretty good. Yeah, me. All right. I don't know how long I can maintain that, but anyway. Okay. So multiplied units, 12.1 meters squared to centimeters squared. So this is a given and this is a find. All right, here's what I know. I know there's 100 centimeters in a meter. All right, but these are squared units. All right, so if I want to change it to centimeters squared, I'm going to have to cancel out meters, turn them into centimeters. And then I'm going to have to cancel out meters again and turn them into centimeters, so that when I'm done, this one cancels that one, this one cancels that one, and I get centimeters times centimeters, which is centimeters squared. Okay. So then I can make these true statements. 1 meter is 100 centimeters. 1 meter is 100 centimeters. Booyah! I find out that 12.1 times 100 times 100 is 1.21 times 10 to the 5th centimeters cubed. Way to go, converting. All right. Density. Density is a way to identify matter. You can tell something's density, it helps you identify what it is. Like density of iron is different than the density of copper, so it can help you identify things. And what density is a ratio of the mass of a substance to its volume. Okay, so here's a formula. Density equals mass over volume, or D equals M over V. And so the units could be any unit of mass, so it could be grams, kilograms, pounds, over any unit of volume. It could be milliliters, it could be centimeters cubed, it could be ounces. Right? So any mass unit over volume unit, the one we use most often in chemistry is grams per milliliter, okay? Or grams per centimeter cubed. So since density is a split unit number, we can use it as a conversion factor. Hey, how many grams is in 49.33 milliliters of hexane? Yay, our favorite chemical, hexane. Woo! All right, here's the density of hexane. So here's what we're given. Here's what we're trying to find, grams. So you start with what you're given, 49.33 milliliters. And then density is given in grams per centimeter cubed. But 1 milliliter equals 1 centimeter cubed. So I'm going to start by converting my milliliters into centimeters cubed. And then I'm going to use density, which has centimeters cubed on the bottom and grams on the top, to help me convert. Okay, so 1 centimeter cubed equals 1 milliliter. You might be saying to yourself, that's going to equal 49.33, and you're right. But it's important that I use the unit conversion here. So this means density means 0.65 grams for every 1 centimeter cubed. And that's just the density of hexane. This number would be different if it wasn't hexane. So milliliters cancel milliliters, centimeters cubed cancel centimeters cubed. We're left with grams. So what do? I multiply all that together, and I get 32.06 grams of hexane if we have 49.33 milliliters. Yay! Yay, density! Woohoo! Right. So, how is this all related to moles, which is supposed to be the topic of this video? So, in Indiana, I buy a ream of paper, a gross of bottle rockets, woohoo, and a dozen donuts. So why didn't I just tell you how many things I buy? Well, instead of telling you about 12 donuts, I'd tell you about a dozen, because then I feel like counting them. When I say a dozen, you know I mean 12. In chemistry, we use the mole, okay? So a gross of bottle rockets is 144. A ream of paper is 500 pieces, right? So do I want to count out 500 pieces of paper? No, I just want to buy a ream, or a gross, or a dozen. So what do we do in chemistry? We use a mole. Yes. Here's what a mole means. It means 6.02 times 10 to the 23rd. That's a huge gigantic number. Look at that. 6.02 and all those zeros. So why is it so huge? Well, atoms are tiny. Atoms are very, very tiny. Very, 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 very so small, tiny. So there are going to be this many atoms in a mole. So even though it's hard to count that many things, we know that there are that many things in a mole. This number has a special name, 6.02 times 10 to the 23rd. It's called Avogadro's number. Right? And it means 1 mole. Just like 1 dozen means 12, 1 mole means this many pieces or particles. All right. So what's a mole? A mole is a unit of measure. It's also a tiny animal that burrows in the ground, as this is a moletato. Moletato. All right. Now I know you're thinking potato, but look, it looks like a mole. See the mouth and the eye and the nose. It's totally a moletato. All right. Anyway, a mole is a unit of measure. It's something we're going to use in chemistry to help us relate between particles and mass and volume. Okay. So how many things are in a mole? Oh, cookies. How many molecules are in a mole of water? If you're saying 6.02 times 10 to the 23rd, you're right. How many atoms of helium are in a mole of helium? If you're thinking 6.02 times 10 to the 23rd, you're right. How many times would you like to see methane bubbles on fire in a mole of times? 6.02 times 10 to the 23rd. Okay. How many pencils are in a mole, 1 mole of pencils? 6.02 times 10 to the 23rd. Now that's ridiculous, because if there were that many pencils on Earth, we would not be able to breathe. I think it would crush the Earth. Okay, that's a lot of pencils. Anyway, gases have an odd feature. If you have a gas that's at the same temperature and pressure as another gas, and it has a certain number of particles, if you have 1 atmosphere of pressure and 0 degrees Celsius, if the volume of that container is 22.4 liters, we know it's a mole. Okay, so 1 mole of any gas at 1 atmosphere pressure and 0 degrees Celsius, also called the standard temperature and pressure, is 22.4 liters. So the number of particles in a gas, if those gases are at the same temperature and pressure and taking up the same amount of space, it's the same number of particles. So the particles are so small that they don't really matter in terms of gas volume. And so at standard temperature and pressure, 1 mole of a gas will always take up 22.4 liters of space. I know, sounds crazy. Here's another thing about a mole is that it's easier to weigh stuff than it is to count stuff, right? So we measure mass in grams, and then we can use the periodic table to tell how many grams are in 1 mole of each element. So when you see this number, which is average atomic mass, it actually tells you how much 1 mole of carbon weighs. So this is how much Avogadro's number of carbon atoms weighs. This is how much Avogadro's number of nitrogen atoms weighs. This is how much 1 mole of oxygen atoms weigh. This is how much 1 mole of silicon atoms weigh. Okay, so all of the molar masses on the periodic table, you can go get grams, and you know how many is a mole. Okay, so we call this a lot of different things, but they mean the same thing. Molar mass, molecular weight, atomic weight. Those all mean the same thing, how much 1 mole weighs. Okay, so how much does 1 mole of carbon weighs? 1 mole of carbon equals 12.01 grams of carbon. Okay, I like to round to 2 decimal places. I know there's 3 on here, but we'll go with standard 2. How much does 1 mole of carbon dioxide weigh? Well, we have in a mole of carbon dioxide, there's 1 mole of that and 2 moles of that. So we got 12.01, 16.00 times 2. So we're going to get that 1 mole of carbon dioxide has a mass of 44.01 grams of carbon dioxide. Is there more? You bet there is. This is aluminum oxalate. So this one's tougher. There's parentheses. There's a lot of subscripts. But it's still the same thing. Here's aluminum. Here's carbon. Here's oxygen. But there's 2 aluminums. So we are going to have 26.98 times 2. Plus there's 6 carbon, so 12.01 times 6, plus there are 12 oxygen, 16.00 times 12, and we find out that 1 mole of aluminum oxalate is going to be 318.02 grams. So we're making an equality. 1 mole of Al2C2O43 equals, I already wrote it, 318.02 grams. Can we do it for other things? You betcha. Oh, look, it's ammonium sulfide. Woohoo, ammonium sulfide. All right, so how do we figure out how much 1 mole of this weighs? Well, we have 14.01 for nitrogen times 2 because of the subscript plus 1.01 times 8. So I should label these. This is aluminum, this is carbon, this is oxygen. This is nitrogen, this is hydrogen, plus sulfur, 32.07, using sulfur right here, 32.07. We find out that 1 mole of ammonium sulfide weighs 68.17 grams. Equal of, and this is only for ammonium sulfide. Right? This is 1 mole of ammonium sulfide. All right, so this is only 1 mole of aluminum oxalate, right? And this is only 1 mole of carbon dioxide. That's only 1 mole of carbon. Okay, so here's what you should remember. 1 mole equals 6.02 times 10 to the 23rd representative particles. What are representative particles? Atoms or molecules, right? What else? 1 mole equals the mass in grams from the periodic table. Mole can be a lot of things. There's 3 ways to talk about the mole. 1 mole equals 22.4 liters, and this is of gas. Only of gas at standard temperature and pressure. Okay. Keep going. Let's calculate moles. All right. Oh, look. All right, we have to remember that stuff. So we need to use dimensional analysis, first part of the video, to convert grams into moles. All right, so given grams, find moles. All right, so start with the given 12.5 grams of carbon dioxide. Okay. I need to find moles. I have to figure out that 1 mole of CO2 weighs what? I did on the last slide, 44.01 grams CO2. Where did I get that? PT, baby. All right, I add up carbon and oxygen for the PT. So now that I know that's true, put grams on the bottom, get rid of it. Moles on the top, turn into it. And then 1 mole equals 44.01 grams. Goodbye grams of CO2. Hello moles of CO2. Simple as that. We get 0.28 moles of carbon dioxide. Okay. Convert, given 19.9 grams, moles of oxygen to grams. Find grams. Now here's what I want you to know about oxygen. It says oxygen. We know oxygen is always O2 when it's by itself. So the given 19.9 moles of O2. Oh, look, I abbreviated it MOL. Can you believe it? That's the abbreviation for mole. Okay. And then I need mole of O2, gram of O2. Where do I get the equality of moles and grams? Well, the number 1 goes with moles, because look, the number 1 is with moles. I have to go get grams from the periodic table. It's going to be 32.00 because it's 2 oxygens, all right? So 2 times 16.00. All right, so moles of oxygen are going to cancel. And then 19.9 times 32 is going to give us 646.8 grams of oxygen. Right? Is there more? You betcha there's more. Okay. So this isn't really simpler. It's just similar. Okay. This is what we're given. 3.559 moles of ammonia as what mass? Find mass. So find grams. Ammonia is NH3. Okay. So you have to state 3.59 grams of NH3. We got to change it into moles, so I got to go grams to moles. Notice it's NH3. All right, this is only going to be true if it's NH3 because I'm going to the periodic table. I'm getting 14.01 for that, 1.01 for that times 3. Looks like it's going to be 17.04 grams for every 1 mole. Goodbye grams. Hello moles of ammonia. Boom. 3.59 divided by 17.04, 0.21 moles of ammonia. All right. Another one. How many moles is in 63.8 liters of helium? Find moles. That's what we want to find when we're done. Given liters. So usually we write down the given 63.8 liters. Talking helium this time. All right. I want to cancel out liters and put it down here. We're still talking about helium. I want to change it to moles. Moles of what? Moles of helium. Important. We got to know what substance we're talking about. Here's where you can look back up here and say 1 mole is 22.4 liters. 1 mole is 22.4 liters. Now, why did I not go to the periodic table? Because this time, it was liters, and liters is going to be a constant. 1 mole is 22.4 liters. Okay, so I would just do 6. Oh, wait a second. 63.8. Sorry, not wait. 63.8 divided by 22.4. It's going to give us 2.85 moles of helium in that 63.8 liters. Okay, so here's what we did. It seems like a long time ago we started, but it wasn't that long ago. Moles are groups of particles or anything that have Avogadro's number of representative particles, 6.02 times 10 to the 23rd. Avogadro's number. Okay. Molar mass is how much a mole weighs, so you got to go to the periodic table and get the grams. So if you memorize what a mole means and know what it equals, we can do mole conversions. 22.4 liters is how much a mole of a gas is at STP. 1 is the number that goes with moles and mole conversions. And then, since we know dimensional analysis, we're going to solve problems and make sure each conversion factor is true. So whenever you write something at the top or bottom, you got to make sure the numbers match. So let's say let's go with liters and milliliters. Well, we have to make sure this is true. We would have to put 1,000 here and 1 there. Okay, so make sure you're looking at chapter 8 in the book and that you can use all these. Okay, peace out. See you guys soon.